Hello and welcome to Add-on. So today we will learn about the atomic packing fraction, and after that we will calculate the atomic packing fraction for BCC, body centered cubic, and FCC, which is face centered cubic crystals. So let's start. What exactly is the atomic packing fraction? Think of APF, or the atomic packing fraction, as the amount of space inside a crystal structure that is actually filled by atoms. It's like thinking, suppose this is a box and there are some marbles, right? So, how much of this box is filled with the marbles versus the empty space? So, mathematically, APF, or atomic packing fraction, is defined as the ratio of the volume occupied by the atoms, which is spherical in nature, and the divided by the total volume of the unit cell. So the formula is given by APF equals to capital Z V small v divided by capital V. So Z is the effective number of the atoms in a unit cell, and V is the volume of a single atom, which is treated as a sphere, and capital V is the total volume of the unit cell. Right? Now that we have understood the formula for atomic packing fraction, we will move on to calculate it for BCC, which is body centered cubic crystal. So let's start. So in BCC structure, there are two atoms per unit cell, one at the center, right here, and one spread across the 8 corners. So what is Z? Z will be equals to 2 in this case. And the volume of a single atom is considered as small v and is given by 4 by 3 pi r cube, which is the volume of sphere as the atom is spherical. And A here is 4 capital R by root 3, which is the distance of the unit cell. So what is the volume of the unit cell? It's V equals to A cube. And what is A cube? A cube is equals to 4R by root 3 whole cube, which is equal to 64R cube divided by 3 root 3. Right? So we will substitute this value in this equation of APF, which is atomic packing fraction equals to ZV divided by V, which is the volume of the unit cell, equals to 2 multiplied by 4 by 3 pi r cube divided by 64 by 3 root 3 multiplied by r cube. So after cancelling out the terms, we have this equal to pi root 3 by 8. Right. Now, after substituting the value of pi as 3.14, we get APF for BCC structure equals to 0.68, or we can say 0.68 multiplied by 100, 68%. So what is this 68%? It means 68% of BCC structure is occupied by atoms and the remaining 32% is empty space. So now that we have understood the packing fraction of BCC crystal, we will move on to calculate it for the FCC, which is face-centered cubic crystal. So let's start. Now let's look at FCC. In FCC crystal, there are 4 atoms per unit cell. How? 1 on each face center plus 8 atoms shared between the cells at each corner. Right? So what is Z? Z will be equals to Z equals to 4. And what is the volume of the atom? It is still V equals to 4 by 3 pi r cube. And what is A here? A for this case is 2 root 2 r. Now what will be the volume of the unit cell, which is given by capital V equals to A cube, similar to the body centered one. So we will take the cube of 2 root 2 r whole cube, which is equal to 16 root 2 r cube. This is the volume of the unit cell. Now, after putting this value in the equation for atomic packing fraction, which is given by we have APF equals to ZV by V equals to 4V by A cube. Now substituting the values, we have 4 multiplied by 4 by 3 pi r cube, which is the volume of a sphere, divided by 16 root 2 r cube. Now after cancelling out the terms, we have equals to pi three root 2. Now after substituting the value of pi, we have APF equals to 0.74 or 0.74 multiplied by 100, which gives us 74%. Now what does 74% mean? That means 74% of the FCC structure is occupied by atoms, leaving 26% of empty space. So to wrap up, we found out that BCC crystal have APF equals to 68%, and for FCC crystal, it is equals to 0.74 or 74%. But why is this difference? Well, FCC has a more efficient packing arrangement than BCC, filling up more space than any other type of crystal. So why might some materials prefer FCC over BCC or vice versa? Think about it. So we will meet in the next videos. Thanks for watching.